Chapter 1.3, More on Functions and Their Graphs. So in this chapter we're going to follow in the same theme as the previous chapter. It's basically like a to be continued of that of chapter 1.2. But we're going to go over some more about general function information. Specifically, this chapter is a little bit more organized. It's about graphing those functions. So a little bit more about graphs specifically as they pertain to functions. So we'll talk about increasing and decreasing, finding maximums and minimums, symmetry, even versus odd functions, as well as piecewise functions. You'll notice here that part of the objectives of chapter 1.3 are going over the difference quotient, but we covered that in chapter 1.2 already, so when you're working on the homework for this chapter, you might want to go back and look at the slides for chapter 1.2 instead if you're not sure what the difference quotient is. So first, we're going to start with interval notation. So I said previously that when dealing with when we're dealing with sets of things on a number line, such as saying a domain is x is greater than 3, or x is less than 7 and greater than 5, etc., we were using what's called inequality notation, using our inequality symbols. But from now on, we're mostly going to use what's called interval notation instead, because this allows us to better represent intervals of numbers on a number line. So this is the more proper notation for that. There are other quote-unquote proper notations that one can use, but inequality notation, at least plain inequality notation as you know it, is not proper. So we will just be dealing with interval notation. So, interval notation allows us to describe a set including all numbers between two given points. We will use the symbols of what are called square brackets to include an n number, like less than or equal to and greater than or equal to do. So to write a is less than or equal to x, which is less than or equal to b, we would write square bracket a, comma, b, square bracket. Those are sort of equivalent statements, or at least that's how we would represent that section of a number line using interval notation. So it's just saying from A to B, but we're including both A and B. But if we're not including A or B, then we would use open brackets or round brackets. So sometimes, so there are a lot of names get used here. They're parentheses, that's all they are. So we have square brackets, also known as closed brackets, and then round brackets, open brackets, or parentheses, they're all the same thing. So those exclude a number. So that's saying A is less than X, which is less than B, and so we use parentheses to say from A to B, but not including A or B. Always remember to write the smaller number on the left and the larger number on the right. This is something that people that a lot of people get confused about, especially when we start involving infinities. You'll see always write it in order. This is numerical order, so this isn't new information. Just make sure you're using the proper notation or else it gets confusing. So proper order. Notice here that I'm saying 2 is less than or equal to x, which is less than 5. You can combine your square and your round brackets. That's fine. So here it's closed on one side, it's open on the other. Which means we're including one side and we're excluding the other. We use infinity to include all numbers greater than a point. So if I'm saying x is greater than a, I would write from a to infinity, not including a, but notice that this is also not including infinity. No matter what, every single time when you're writing this, when you have infinity in your interval, should always be a round bracket. Similarly, negative infinity, if I have x is less than or equal to b, I have parenthesis, negative infinity, comma, b, closed bracket. Because I included b, we can never include infinity. So both times, it's a round bracket no matter what. If you ever write a square bracket here, it's incorrect. It will always be a round bracket. Just think, infinity is round, bracket is round, just go with that. Essentially, the reasoning for that is because we cannot include infinity, as infinity is a concept and not a number, so it can't have a hard stop to it the way the closed bracket gives us. It gives us a hard stop, and you're not stopping at infinity because infinity never stops. That's why we use the round bracket, so that we're not stopping somewhere. Then to combine intervals, if I have x is greater than 3 or x is less than or equal to 1, so that's two different intervals, we use the union symbol, which just looks kind of like a capital U. So it isn't actually a capital U, it's a little bit different, but in essence it is. You can draw it as a capital U. So we will write one of these intervals. Remember that x is less than or equal to 1 would be from negative infinity to 1, including 1. And then x is greater than 3 is 3 to infinity, not including 3. So we just write the union symbol between them to say that we are combining these two intervals. Both of these intervals are our answer. So if you don't write the union symbol, or you write a comma between them, what you're doing is you're listing intervals, you're not combining them, so technically it is incorrect. Will I mark it wrong? It depends. On the final exam, it would definitely be marked wrong, but sometimes I'll be nice on labs, etc. But generally, you want to remember to use that union symbol. Alright, so now that we have our notation for writing intervals, we're going to talk about how we can use those intervals, different problems that would involve them. So, as I said before, dealing with domain and range, we can definitely use our interval notation to write out our domain and range. We can also use interval notation to talk about where a function is increasing, decreasing, or constant. So, when looking at a graph, a function is called increasing if it slopes upward. So, if I can draw any line here, and it's clearly going up, right? It's increasing here. It's also clearly going up here. Like, if I draw these tangent lines, we can see that it is going upward. But it is decreasing whenever it's sloping downward. So even though these are not linear, these are not straight lines that are occurring, these are not always the same slope even. Like, the slope here is going to be very different than the slope here, which is going to be very different than the slope here. You can see that the curve is changing, or the slope of the curve is changing. That's fine, it's still going up. Whereas here, first we're going down, and then we're going down like this, and then we're kind of coming back to the way we were, but we're still going down. So it is decreasing. So we write in interval notation that it is increasing from negative infinity to negative 2 and 2 to infinity, and we put the union symbol between those. And it is decreasing from negative 2 to 2 and nowhere else, so we don't need to do anything else there. Notice that I'm not including those endpoints though, just because technically at these points, if I was to draw the tangent line to this point, it would be a flat line, so it is not increasing nor decreasing, it is flat. And what is flat? Flat means it's constant. So if it is flat, neither increasing nor decreasing, we say it's constant. So so technically it is constant at those points, those endpoints, but generally you're not going to be asked that. Usually we're looking for constant if it's part of our graph looks like this, and here would be where it's constant, etc. So next thing we can talk about on a graph is finding local extrema. So we have a very similar graph here. What is an extrema though? Well, a function has a local, also known as relative. You will see both of these words interchangeably. Extremum, which the plural of that is extrema, at a point if it is increasing on the left, decreasing on the right, gives us a local or relative maximum. So here can say this is the maximum point, or the local maximum point of this area of the function. Yes, the function itself goes off to infinity. If I was to write the range of this function, it would be going from negative infinity to positive infinity. But in this area, this point right here is the maximum. So it is called a local or relative maximum because it is local in this relative area. It is a maximum in this relative area, in this local area. So around the area around it, even if it's just a small, tiny, tiny little area around it, and then it shoots back up, it doesn't matter. The point is that if you can make an interval where it is the maximum of that interval, an open interval, then we have a relative or local maximum. Similarly, a local or relative minimum is where we are decreasing on the left and then increasing on the right. So here we have the local minimum is negative 16, which occurs at x equals 2. So once again, note that I'm stating that the minimum is negative 16. We can also say the local minimum occurs at x equals negative 2 or at the point negative 2 comma 16. Any of those are correct, but do not say the local minimum is 2 because that's wrong. The minimum is not 2. The minimum value that occurred was negative 16. It's all about the output here. So our local minimum is negative 16. Even though our function goes off towards negative infinity, our range would keep going, and so this is not the minimum value that the function achieves. We've clearly got points where y is equal to negative 20 and negative 50 and negative 1 billion. All of that is included in here, but for this area of the function, for some interval of this function, negative 16 is the minimum. So it is called a local or relative to that area minimum. So note that these local extrema are just the most extreme points in a given area. They can be, but do not need to be the maximum or minimum values the function reaches. So now for some formal definitions of these things we've gone over. So a function f is increasing on an open interval if f of b is greater than f of a for any two input values a and b in the given interval where b is greater than a. So essentially here we're just going to go through a lot of formal definitions of all of what we just went over. Pay attention to the pictures a little bit more than the formal definitions. The formal definitions definitely matter, but as long as you understand the concepts, the formal definitions are just there as a guide. So essentially what this is saying is that we're increasing as long as no matter what 2 points I pick in that function, the output values have, the output value of the smaller value of the smaller input is smaller, and the output value of the larger input is larger. That means we have increased. Whereas we have decreased if the output value of the smaller value is larger than the next output value. If we have gone down in our output values, then we are decreasing. That's all this statement is saying. So if f of b is less than f of a for any two input values, a and b, where b is larger than a. Similarly, a local maximum occurs at x equals b if there exists an interval from a to c where b is in the middle of them, such that for any x in the interval, f of x is less than f of b, or less than or equal to f of b. So it is a local maximum if every other output value within that interval is less than this output value. And it's a local minimum if every other output value in some interval around it is greater than the output value of f of b. So remember the output value being y, meaning the y value, f of b is y, etc. So you don't necessarily need to memorize all of these formal definitions, but you do need to understand them conceptually, and so that's what all of the graphs from the previous slides were about. So how do we find extrema using a graphing calculator? This is something you'll need to know for the future. So to find a local extrema of f using a graphing calculator, we can first graph the function on the calculator. So once you have the function graphed on your calculator, so you go into y equals, different calculators look a little bit different here, but if you have trouble with your calculator, please let me know. Generally, you're just looking for where it says y equals. On my calculator, it is the top left button. Right hard to see, right here. So we graph the function on the calculator, so we're going to write out this function. Then we're going to identify where the function is increasing and decreasing. So once we look at our graph, which you can look at your graph top right button right here by clicking graph, you might have to adjust the window. So there's a window button, also top second from the left now. So again, for calculator help, please let me know. You will need to know how to use your calculators for the tests, so if you don't know how to use your calculator, that is something I can definitely teach you, but it's not something that's really covered in the chapters themselves, or at least in the PowerPoints. If you look in the chapters in the textbook, it gives you a little bit more detail sometimes. So from here, once you have your function graphed, we can use the find max or min on your calculator. So if you're using a TI-83 or a TI-84, I have a TI-84 plus C, but they're all basically, they're not the same, but they have the same buttons for the most part. So on a TI-83, you go to the button that says calc, which is second trace. So trace is here, so second trace is calc. You'll see the word calc above it. And then when you do that, you'll scroll down to where it says minimum or maximum, or min or max, it might say, and then hit enter. So whichever one you want, whether you want looking for minimum or maximum, pick the one that you want, then hit enter, and then it's going to ask you to pick something to the left, so it'll say left question mark, so you will arrow over to the left of where you believe the minimum to be, if we're looking for a minimum, and then it'll ask for right question mark, and so you'll arrow over to something that's a little bit to the right of the minimum, hit enter, then you will arrow over, it'll say guess, so you place the cursor right on top of the minimum. This just allows your graphing calculator to know exactly what minimum you're looking for, because functions can have more than one relative minimum. So if your function looks like something like this, it has a whole bunch of relative mins and relative maxes, and if you want specifically what is this point, well then you're going to have to tell it. So you're going to pick a point over here as the left, and you'll pick something over here as the right, and then when it says guess, you'll just try to get close to it so that it really has no ambiguity about what you're asking for, and then it will calculate for you what the x and y value of the actual minimum are. Your guess doesn't have to be accurate, or else what would be the point? It's just another way of showing precise, a guess at what you're trying to find. So in this case, if you want to test yourself, try this out on your calculator. The local maximum of this function occurs at negative 2.449, comma, negative 1.633. And the local minimum occurs at 2.449, comma, 1.633. So test yourself, see if you can do this on your calculator. All right. So we saw these common functions on the previous chapter slides. So I introduced them, and I sort of hinted that they would be important. They're important because they're going to show up in a lot of these chapters. I said you'll need to know how to graph them, but you'll also be using them to sort of identify the information we're learning about functions. So in this case, we'll be analyzing these common functions that you were introduced to see where they're increasing and decreasing, and where their minimums and maximums are, etc. So here, we have the constant function is neither increasing nor decreasing at all. So it is, in fact, constant. You can probably guess that by the name. The identity function is always increasing. It just keeps going up, so no matter what, it's got the same slope the whole time. That's how linear functions work. So it is increasing. Whereas quadratic, it's going down and then it's going up. So it's also got, it's first one we have where we have increasing and decreasing, and it has a minimum at x equals 0, or a relative minimum specifically. It actually has a even better minimum than that. That is the full minimum value of the function, I should say. Then the cubic, it is increasing for the entire time, even though it sort of does this, and then it's sort of like this, and then it slopes up more later. It is increasing the entire time. It never decreases. So just the plain old cubic function, always increasing. But it does not have any relative mins or maxes. The reciprocal function, this one is decreasing and then decreasing again. But notice that we've written our interval as with a union. Even though it is decreasing on its whole domain, its domain is actually this, how this interval, this combined interval is given. So we know we're not allowed to divide by 0. So we have to cut 0 out of our domain. So this function, the reciprocal function, 1 over x, this is 1 over x if you don't remember, is decreasing the whole time, but it's not decreasing at 0 because there is no x equals 0 in this function. So we cut that out of the domain. So we cut it out of its decreasing intervals. And one other note to make is that yes, even though this is decreasing, this is clearly decreasing, here, yes, it went up. Look, the actual value is much higher than it was, but the slope itself is still decreasing. It's still sloping downward. Even though it shot up here and it is higher up, it did not suddenly start increasing, so be careful about that. Then the reciprocal squared, first it's increasing here and then it's decreasing over here. Still no minimums or maximums because when it changed from increasing to decreasing, that point, that x equals 0, does not exist. It is not part of the domain. So normally, we would have a minimum whenever we change from increasing to decreasing, but we can only have a minimum, we can only have a maximum when we change from increasing to decreasing if we have that point at all, if that point exists, which it doesn't here. Next, we have the square root, which is increasing on its entire domain. Again, its domain being from 0 to infinity. Actually, at 0, it is not increasing. It is nothing, even though that is part of its domain. Then the cube root, increasing the entire time. And the absolute value, here once again, decrease, then increase. And so we have a minimum value because we switched over from decreasing to increasing, and that middle point does actually exist. So we have a minimum at x equals 0. All right, so now we've talked about relative or local extrema. Next thing to cover is what's called absolute extrema, which is very related to our relative extrema. The only difference is that absolute extrema is, well, more absolute, but specifically it's not every function is going to have this. You can have a relative minimum or relative maximum without having absolute minimum or absolute maximum. What an absolute minimum or maximum gives us is that no matter what, this is the actual maximum value the function takes. This is the end of the range of the function. So if our range stops somewhere, whether it stops at a maximum or stops at a minimum or both, then we have an absolute maximum or minimum. Absolute in math usually means we're giving some very specific, nothing can break this value. So, here we have the absolute maximum of f at x equals c is f of c, where f of c is greater or equal to f of x for all x in the domain, not on some interval like before. That's the difference. The relative mins and maxes were on some interval, some local area around. We also sometimes call these intervals neighborhoods, just to say it's the area where this point lives. So some area around here, yes, that is the minimum value. But more specifically than that, the range of this function is from here to here. So we get an absolute maximum and an absolute minimum for this function. So the absolute maximum being f of 2 equal to 2, and the absolute minimum being f of 0 equal to negative 2, because our range is from -2 to 2. So that tells us we have an absolute max and min. If our range has closed endpoints like this, has square brackets involved, we have an absolute maximum and an absolute minimum, and it's just your job to say where they occur, but we definitely have them as long as there are closed endpoints on either end, one or the other or both of our range. So a function can have multiple relative mins and maxes, but at most one absolute min and max, because that's the end points to its range. It has one on the left, one on the right. Maybe, at most, it might have none of those. So, for example, in this graph, we now have a relative min. Down here, we have these two right here are relative maxes, but also they are absolute because they happen to be the highest value that this function takes. So our absolute max is 16 and our absolute min is 10. So even though that it occurred twice, we can say the absolute max is 16 at x equals -2 and x equals 2, that's fine, but the max is 16. And the min is 10, but there is still this relative minimum in the middle. Next, we have a sort of, it feels unrelated, it's all still about functions, but we're now moving away from our maxes and mins into another graphing topic, but this one's going to be a little bit more algebraic. So even and odd functions. A function is even if for every input x, f of x equals f of -x. So f of -x, we've talked about how to plug into a function to replace x before. This is something called composition, which is covered in a later chapter, so you'll see that much later, this more in detail, but we're dealing with just even and odd functions. All you need to know is how to plug in -x. So even functions, we can recognize them on a graph because they are symmetric about the y-axis, which means that if I folded my graph in half over the y-axis, then it would be the same on either side. So here we can see if I fold this graph in half, it's the same on both sides. If I did an ink blot test of this, it would be the same on both sides. But an odd function, on the other hand, by definition is f of x equals -f of -x. We can also sometimes say, or we can always say, -f of x equals f of -x. These are the same thing, so whichever way you like to think of it doesn't matter. So what's special about an odd function is odd functions have origin symmetry or rotational symmetry, which means that if I was to pick up this graph and turn it 180 degrees, so this is 180 degrees, then it would be exactly the same, right? So this is x cubed. X cubed has this origin symmetry. If I pick it up and turn it around 180 degrees, it's the same. Whereas going back to this being x squared, if we fold this in half, we get that we get y-axis symmetry, but if I turned it around 180 degrees, it'd just be upside down. So there's no origin symmetry here. So note that a function can be neither even nor odd, but the only function that is both would be f of x equal to 0. So is f of x equal to x cubed plus 2x even, odd, or neither? So that is our question. How do we tell? Well, we use those definitions. We plug in -x, and we check, is it equal to f of x? And if it's not, then we are going to multiply it all by negative to see, is that equal to f of x? And if it's not, then we say neither. So, start off, test for evenness, plug in -x. So when I do that, it just means every x that was in my function is getting replaced with -x. So -x cubed plus 2 times -x. Then I'm going to simplify a little bit. So remember that what's going on here is negative x cubed. So that's negative x times negative x times negative x. That's going to have an x cubed in it, but how many negatives are there? There's 3 negatives. 3 negatives make a negative, right? Because 2 negatives make a positive, and then we have another negative in there. So really, we get x cubed because there are 3 x's, and then a negative outside. So in other words, negative x cubed simplifies to just negative x. Similarly, 2 times negative x simplifies to negative 2x. So we have negative x cubed minus 2x. Now, is that equivalent to the original function, f of x? No, it's not. F of x was x cubed plus 2x, and now we have negative x cubed minus 2x. So they are not equivalent. They are not the same function. So no, this function is not even. Now we test for oddness. So we're going to go negative f of negative x. We already know what f of negative x is. So we just need to apply a negative to everything. So right here, I took this guy right here, and then I just applied a negative outside. And remember, when we apply a negative outside the parentheses, we're going to have to distribute that negative to everything inside. So every single term has to change its sign. So we're getting positive x cubed plus 2x. The negative f of negative x is x cubed plus 2x, which, in fact, is the same as the original function. So yes, this function is odd. And if we were to graph it, we would see it has that rotational symmetry. Now, I can't do that by hand at this moment. If I had graph paper, I could. But if we were to graph this, we would see that rotational symmetry. It's going to look something along the lines of this. Wow, that's bad. Let's try that again. It's going to look something along the lines of this, where we could then rotate it around and get 180-degree rotational symmetry. I encourage you to put this on a calculator just to check that. So when you are asked to test whether something is even, odd, or neither, showing its symmetry is one way to state that it is even or odd or neither. But most of the time you're going to be asked to prove it, and to prove it is to do this, is to do these 2 steps. So if you are asked to prove that something's even, odd, or neither, and you just say it has rotational symmetry, you didn't prove anything. You have to show the algebraic work for our proofs of this type of problem. So if you're asked to tell whether it's even or odd, make sure you're plugging in negative x and multiplying by negative 1 and all of that to make sure that you're getting that actual proof. All right, so the last topic for this chapter is piecewise functions. So this one is often one of the more confusing topics to a lot of people. A piecewise function is a function in which more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is the union of all these smaller domains. So we notate this idea like this. So we'll take f of x equal to, and then a big curly bracket. Notice it's not on both sides, because then we'd have set notation, and that's not really what's happening. This big curly bracket is really just being used to sort of group things together. So we'll have formula 1. X is in domain 1. Formula 2, x is in domain 2. Formula 3, x is in domain 3, and so on. You can have as many or as few formulas as you want to make this piecewise function. Most of the time you'll just see it with 2 of them, but I'm just showing that you can do it with 3 or 5 or 17. It doesn't matter. So, for example, the absolute value function is defined by a piecewise function. Absolute value of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. So this is the actual definition of the absolute value function. And why is that the definition? Why is it written like that? Well, essentially, just think about it. If you know that the absolute value of 3 is 3, so in other words, 3 being within this first domain, 3 is greater than 0, we're just getting out the identity. Absolute value of 3 is 3. But absolute value of negative 3 is also 3. So if I look in this domain, if x is less than 0, negative 3 is less than 0, so I'm in this domain, so I want to use this function, negative 3. So the absolute value of negative 3 is equal to negative 3, which is positive 3, which is exactly what we knew. So here we have a way to say that the absolute value, a way to split the absolute value so that it has these two different functions. Remember in the graph, it's the identity function on one side, this is x, and on the other side, it's actually negative x. So we can see that in the graph, that part of it is basically negative x, and part of it is basically just the identity function. So this absolute value is a piecewise function. But let's explore some further piecewise functions. First, we'll work with a word problem, and then we'll look at how to graph piecewise functions in general. So a museum charges $5 per person for a guided tour with a group of 1 to 9 people, or a fixed $50 fee for a group of 10 or more people. So, write a function relating the number of people n to the cost c. So here we have number of people n, cost c, it's $5 per person, up to 9 people, or $50 for 10. So, we can say 2 formulas are needed. When we have less than 10 people, our first formula would just be 5 times the number of people. So if it's 1 person, it's $5, 2 people, $10, 3, $15, and so on. But when we have 10 or more people, our cost is just 50 flat, and that's it. So instead of having to write this out verbally, we can write it as a piecewise function, where we would have these two intervals. For our function is 5n, when n is between 0 and 10, and it is 50, just flat, constant 50, when n is greater than or equal to 10. So we would know how to plug into this function as long as we know what n is. So if we want to graph the function, we just want to think about these two intervals being broken apart and know exactly what's going on depending on what value of n we are. So again, I'm going to talk about graphing in a moment, but here we have a graph of this function. So c of n is shown here where this area is 5n. This is what 5n looks like. And this one is 50 when we start at 10. So we have broken apart our function over those intervals. So if I want to find c of 5, c of 10, or c of 15, then I just need to plug in 5, 10, and 15 into the proper interval. So c of 5, I can either look at the graph or I can look at my function. In this case, I'm going to look at my function. To plug in 5, all I have to do is look at which interval am I on. So 5 is between 0 and 10, so I'm on this first interval, so I'm going to plug into the first equation. 5 times 5 is 25, so c of 5 is 25, which I should know because it's $5 per person for a group of 1 to 9. So each person pays $5, that's $25. But if there are 10 people, 10 or more people, it's $50. And if I look at my function, when n is greater than or equal to 10, 10 is equal to 10, so I'd be plugging into the second equation. Same for c of 15. I'd plug into the second equation. And so we can see this on the graph as well. So we can either look at the graph or we can look at the function to find these answers. So if you were going to sketch the graph of a function, of a piecewise function, you would have to know how to break it apart into these intervals. So this is, again, most students have a lot of trouble with remembering to break apart these functions. So when you are graphing a piecewise function, remember that these intervals really matter, okay? So when you may know how to graph f of x equals x squared and f of x equals 3 and f of x equals x, but if you don't break it into pieces, then you don't have a piecewise function. In fact, you don't have a function at all. So what we're going to do is we're going to graph each of these pieces on the domain that was given. So first, x squared, when x is less than or equal to 1, which, remember, the domain is negative infinity to 1, then we have, well, this is x squared, but I'm stopping at 1, okay? Then, from 1 to 2, not including 1, we're just the constant function 3. So I'm only drawing that part of the graph. Of course it continues in either direction. Like the whole graph would look like this, whole graph would look like that, and then here, whole graph would look like this. But I don't care about those extra pieces. All I care about is, well, f of x equals x when x is greater than 2. And so that's what I've drawn here, is when x is greater than 2, there's that. Okay, so these are 3 separate graphs. The graph of this function, f of x, is going to be all 3 of them together. And so we have a final answer with a domain, negative infinity to positive infinity, and a range of 0 to infinity. Even though it's not all connected. That's going to happen fairly often with piecewise functions. It doesn't have to be connected. So here we have these breaks, and that's why it's very important to pay attention to whether we have an open circle or a closed circle. Because if both of these were closed, we wouldn't have a function, because we would fail the vertical line test, which I have drawn this vertical line very poorly. There we go. We would fail the vertical line test because we would hit 2 points. So this has to be open if this one is closed. This has to be open if this one is closed, to make sure that we are still a function, that our domain never repeats anything if they aren't overlapping in some way, if there's this disconnection there. So with that, we have finished chapter 1.3. Again, I know this was a long one. These early chapters are a lot longer than most of the chapters in the textbook. So hopefully you were able to get through this without in one sitting, maybe, but maybe it took a couple sittings. That's entirely fair. So here again, we have some practice problems with their answers. I encourage you to go through and do some practice and make sure you are understanding what's going on.